Hi class, this is Dr. Martino. We're going to be starting the respiratory chapter. This is the most challenging chapter in physiology for most students, and this has been true, and I have taught this at the community college level, at the technical college level, small undergrad institutions, medical school, nursing school. It's always the case, graduate school, that this seems to be the system that gives students the most trouble. So technically it's challenging, but it is doable. So let's get right into it. One of the things you're going to have to do in this chapter early on, much like the cardiovascular system, is you're going to have to go through and review from basic chemistry, basic laws. Some of these we'll review as we go through the lecture: Boyle's law, Dalton's law, Charles' law, Avogadro's law, Gay-Lussac's law, law of Laplace. That may be a new one for you. We're going to talk about what transpulmonary pressure means, chest wall pressure, driving force of movement of air in and out of the lungs. What's the difference between minute ventilation and alveolar or pulmonary ventilation? You should memorize the gas percentages in the atmosphere. Roughly 78% of the atmosphere is made up of nitrogen, 20.78% is made up of oxygen, 0.93% of argon, and 0.04% of CO2, and then there's minuscule amounts of helium and hydrogen and the other gases. Atmospheric pressure at sea level is about 760 millimeters of mercury. In the Milwaukee, Chicago area, we're probably looking at about 750, 745 millimeters of mercury pressure, depending on the day, because we're about 600 feet above sea level. And we're going to talk about converting atmospheric gas percentages to partial pressures. There's different sections of the respiratory system in terms of thought. There's the mechanics of the respiratory system, and that's the part that seems to give most people issues. There's a little bit of math, although we're not going to spend a lot of time doing a lot of math, but it's relatively simple math, but conceptually challenging. So that's one big area, the mechanics. And then you have the actual physiology of breathing and what happens in the tissues. And then, of course, you have O2 saturation, which is another big section. So let's get to it. Basic functions of the respiratory system. Most or all of you know that it provides oxygen. When you breathe in, you bring in the most important gas that comes in is oxygen. And when you breathe out, you eliminate carbon dioxide, CO2. The respiratory system functions to regulate the blood hydrogen ion concentration, or the hydronium concentration, or the pH, in coordination with the kidneys. So there are two systems that regulate pH in the body. The first line of defense is the respiratory system. That's your most immediate tool to regulate pH. And then the long-term system is the renal or the kidney system. Obviously, the respiratory system is involved in the formation of speech sounds, phonation. You defend against microbes. There's a large amount of innate and adaptive mechanisms that occur specifically in the lungs, because much like the digestive system, it is being exposed and bombarded by bacteria, viruses, fungi, other kinds of parasites and critters. So you can defend against microbes. It influences the arterial concentrations of chemical messengers by removing some of the pulmonary capillary blood and producing and adding others to this blood. So how much of chemical messengers, all kinds of chemical messengers, are in the blood depends on how much is removed from the blood, right, and added. The respiratory system also traps and dissolves blood clots arising from systemic veins, such as those in the legs. So most of the time, there is no problem with things like deep vein thrombosis. This is a basic diagram here. It goes through ventilation, exchange of O2 and CO2, transport of CO2 and O2, exchange of O2 and CO2 at the cellular level, and then utilization. So airflow into the lungs is called ventilation. Air that is exchanged with the capillaries in the lungs via the alveoli and the lung capillaries is called exchange. And then you have different levels of transport and exchange, respiration. So you have ventilation, which is defined as the exchange in air between the atmosphere and the alveoli by bulk flow. Exchange of O2 and CO2 between the alveolar air and the blood in the lung capillaries by diffusion. Step 3, you have a transport of O2 and CO2 through pulmonary and systemic circulations by bulk flow. 4, you have exchange of O2 and CO2 between the blood tissues, capillaries, and cells. And then you have the cellular utilization, which is cellular respiration. Right, so those are the 5 steps. And then you have the reverse that occurs, right, from 5 through 1 on expiration. So inspiration, expiration. You can see in this diagram here that the O2 comes in, it enriches the venous blood that is coming through the capillaries so that it is reoxygenated, so it's fully oxygenated to be about 100 millimeters of mercury pressure of O2. And that's why you see here that the color is changing from a bluish purple to a more red. And you can see the blood flow. You've already learned about the blood flow through the body and through the lungs, so we're not going to repeat that. Ultimately, this blood goes to the left heart and is pumped throughout the body. And so this sequence of events here explains what happens. You should memorize that, know it backwards and forwards. Basic anatomy, right? You have the nasal cavity, the nostrils where you can breathe through. You have your mouth. You have the larynx where the voice box is located. And above the larynx, you have the pharynx, which is soft tissue. Oftentimes the tongue and the pharynx are problematic in people that have something called sleep apnea. And we can talk about that later. And right above the larynx here, you have the glottis, right? The epiglottis and the glottic aperture, the opening that separates the trachea, which is anterior to the esophagus, right? And the epiglottis folds over the trachea so that when you swallow food, food can go down the esophagus on the posterior end of the neck versus the trachea, which is the anterior end of the neck. The trachea has all of these rings. These cartilaginous rings make the largest air tube in the body extremely difficult to collapse. And then that airway then splits into 2 bronchi, the left and the right bronchus. And then you get a continual branching. You have bronchioles, and you go down multiple levels until you eventually get to the alveoli, which are the small air sacs. The diaphragm is the primary driver of inspiration and expiration. It is a dome-shaped muscle that separates the thoracic cavity from the abdominal cavity, right? And in this shape here, This person has just finished exhaling, because when you inhale, the diaphragm tends to bow down a little bit, and when you exhale, it bows up. So you should know that. This is a picture of the airway inside the trachea. Here you have the epiglottis. Here you have the tongue. And so here's the airway. The epiglottis covers the airway. And when doctors have to intubate a patient, they have to be able to maneuver the tongue out of the way with something called a laryngoscope, and wait until the person takes a breath in, so that the epiglottis will get out of the way of the trachea, and then the endotracheal tube can be placed inside the trachea, as opposed to accidentally placing it in the esophagus. This is someone with a tracheostomy. So this person has some kind of issue with their pharynx and their larynx, this area up here, and they're not able to breathe well. So this could be due to things like COPD. Likely this person would have been a smoker that has done damage to the upper airway, and that's what this area is called, the upper airway. There's lots of reasons. This person could also be a quadriplegic who's had to have the airway bypassed. So this is something that happens. It's not natural, it's not normal, but it is a way to bypass this part of the respiratory system, this upper part of the respiratory system here, so that a person can breathe. Here is the branching sequence of the airways. Remember, the trachea is the largest airway. So from the trachea to the terminal bronchioles, this is called the conducting zone. And then from the respiratory bronchioles down to the alveoli is the respiratory zone. In the conducting zone, there is no air exchange between the body and the airways, right? They're just tubes. This is where dead space comes into play mostly, although there is dead space throughout the system. So you've got the trachea, there's one, there's bronchi, there's two, and then there's different levels of bronchioles, right? And you can see how this starts to become exponential. Terminal bronchioles. Finally, by the time you get to the respiratory bronchioles, you get some gas exchange between this airway and blood vessels, alveolar ducts, which lead to alveolar sacs, and the majority of the gas exchange occurs between the alveoli. I can draw this, I think. I hope. Between the alveoli, and this is an example of a capillary, right? These capillaries would actually be surrounding the alveoli. So oxygen can come in to the capillaries, and CO2 can leave. So the majority of gas exchange occurs between the alveoli and the capillary. So the average person has roughly a surface area of lung capillaries and a surface area of alveoli, each being about the size of a tennis court. So that enormous surface area allows gas exchange to occur in about a quarter of a second. Table 13.2, functions of the conducting zone. I'll read through this. Provides a low resistance pathway for airflow, right? You don't want to have high resistance that makes it hard to breathe. The resistance is physiologically regulated by changes. So when you think about resistance, think about friction. The friction of airflow against the tubes, right? And you want to have as little resistance as possible that makes it as easy as possible to breathe. In diseases, in conditions that are caused by activities like smoking, other diseases like asthma, COPD, you can have an increased resistance to airflow in the airways due to increased friction, and this makes it more difficult to bring in enough oxygen and eliminate CO2. The airways, the smaller airways, are actually surrounded by smooth muscle that allows them to dilate and constrict. The conducting zones, most of the conducting zones, at least the larger parts of it, are surrounded by cartilaginous rings that prevent them from collapsing. Remember that the conducting zone defends against microbes, toxic chemicals, and other foreign matter. There are cilia, there's mucus, there's macrophages. This is part of the innate immune system. The conducting zones warm and moisten air. So do the nasal passages. That's why they're turbinated, right? You have the superior, middle, and inferior turbinates that you would have learned about in either Bio 3300 or 2010, 2020. And that's important that we moisten air. And allows for phonation, which is where the vocal cords are located. So this is the conducting zone. Gas exchange occurs in the respiratory zone. Remember, the respiratory zone is located here, right? Mainly in alveolar sacs. There are about 8 million alveolar sacs. Massive surface area, again, like a tennis court. These numbers, if you go read, you go to Wikipedia, there's a range per lung alveoli. I mean, I've read anything from, in other textbooks, some state that it's 8 million, some state that it's 10 million, some state that it's 15 million. It's probably all of those. And there's right, in every anatomy and physiology trait that you can come up with in an animal follows a bell-shaped curve, right? So if 8 million happens to be this area here, you can imagine on this side you'd have, 15, 20, 30 million, and down here you'd have 6, 4, 2. These are more rare probably, but there is a range. Muscles of ventilation. Real basic. We should remember that there are muscles, multiple muscles, again, under normal eupnic, resting breathing, quiet breathing, the diaphragm, this dome-shaped muscle that sits underneath the rib cage, is the main driver, right? Take a deep breath in, the dome comes down, exhale, and the dome goes up. So why do we have these other muscles? The abdominals, the rectus abdominis, the deep abdominal muscles, the transverse abdominis, the intercostals, the external and internal intercostals are all involved in situations where you need to move air much more quickly, and so the diaphragm needs help. So you can imagine under circumstances like exercise, let's say you go out for a run. The harder or the faster you begin to run, the more metabolic need there's going to be for oxygen, and the more carbon dioxide you're going to produce from your cells that need to be eliminated, and the faster you're going to have to move all of that. So in order to help the diaphragm muscle in this process, you now start to add in the internal intercostals, the external intercostals, transverse abdominis, rectus abdominis, the obliques. If you've ever done running, okay, if you've ever done running, there would have been a first time where you ran. And probably what happened to you, especially if you did this in a competitive environment where you're being coached, After that first running training session, you probably notice that your ribs and your upper abdominal area hurt, and that is because these muscles, these intercostals, transverse abdominis, the obliques, aren't normally being used to run around. Now, this wouldn't be so much true for small children who are very active because they run around quite a bit. But if you started to do this, let's say even as a young high school young man or woman and you hadn't been super active, then you would have experienced this soreness, and that soreness is from these muscles being used at a level that they hadn't been used before. So the bottom line is the major muscle that drives breathing under eupneic, under quiet breathing, most of the time when you're walking around, is the diaphragm muscle. The other muscles are there as ancillary, accessory muscles in times of greater need. So for inspiration, you've got the diaphragm and the external intercostals. Both of these muscles are going to cause the chest, as you can see here. So you've got this chest here is under inspiration, right? And what happens is as the dome comes down, the chest expands and the external intercostals expand the ribs distance from one another, right? And so everything gets bigger. And when you breathe, here's another misconception. You shouldn't be breathing up or down. You should be breathing a big belly breath, and the breath should be going in 360 degrees around your torso. Most people do not breathe correctly. It is something we've forgotten how to do, and it seems ridiculous to say that people don't know how to breathe, but that is true, and it causes lots and lots of problems in our society, and part of it is due to sitting. So if this is inspiration, the chest gets bigger and comes down the diaphragm, right, and expands. Then when you expire, the diaphragm moves upward, the internal intercostals get involved, and the chest constricts. So the chest, the ribs, because of the cartilage and the way they're designed, are able to expand and contract within a range. This is one of the important concepts that we're going to have to get through to each and every one of you, because the chest wall rigidity, how rigid that chest wall comes into play in mechanics when we get there. Okay, so expiration is normally passive, so you need the muscle, the diaphragm muscle, to contract, which brings in air, right? Which starts the process of bringing in air, and we're going to talk about all the pressures involved. And then when you're done bringing in that air, you expire normally under passive conditions. You just relax the diaphragm, and the chest wall and the lungs, which are elastic, there's some elasticity to them, recoil. And if you think about elasticity, you think about a strong rubber band. And the harder you pull that rubber band out, the more it's going to snap back. Well, the chest wall and the lungs both have that quality too. Other things we should know about the lungs and the chest wall as a unit. The lungs are attached to the chest wall via the pleura. Pleura is very different physical characteristics. And so the pleura, right, this is the chest wall, and here's the lung. Okay, so this is the lung, and this is the chest wall. Imagine that there is a water gap here. This is the pleural space, and this pleural space is what connects the lung and the chest wall. If you have a breach, if a hole is inserted into the chest wall, this water gap dissipates and the chest wall, which is holding the lungs open, no longer can do that, and you get a collapsed lung. A pneumothorax, it's called. Okay, let's move on. So the chest wall is rigid and holds the lungs open. It wants to hold the lungs at 60% of total lung capacity. We're going to go through the basic capacities and volumes. Again, something else you need to memorize. So total lung capacity is the total amount of air that your lungs can hold, and that's set at 100%. And so the chest wall wants to hold the lungs open at about 60% of their capacity. The lungs are floppy bags of meat. They're essentially rubber bands, and they want to completely collapse to 0% TLC. So the equilibrium point between the two is at about 40% total lung capacity. So those are numbers you should know. Here's another example describing the pleura and the relationship between the lungs and the chest wall. If you take a fluid-filled balloon and you push your fist into it, the fist represents the lungs. This is the pleural space. And then this outside area here represents the chest wall. You can see this here. You have the parietal pleura. Imagine that the chest wall is here. Right. Visceral pleura is the space or the membrane that's directly connected to the lung, and the interpleural fluid or the interpleural space, this is what connects the lungs here and the chest wall again here. Of course, you've got the heart in this space here. Here's the thoracic wall, and you've got the trachea and the bronchi. So the space inside the lung is filled with air, but the interpleural space is filled with fluid. So you have a air to fluid interface. So movement of the thoracic wall, you can also put in for thoracic wall, the chest wall, right? So the thoracic wall, the chest wall, drives ventilation. The intrapleural pressure, so the intrapleural pressure, the pressure in this space here is abbreviated big P for pleura, pressure, excuse me, and IP for intrapleural pressure. This pressure is always negative compared to atmospheric. It sits at about -4 centimeters of water. When we've been talking about the cardiovascular system, we've been measuring pressures in terms of millimeters of mercury or torr. In the respiratory system, we typically measure pressures in centimeters of water. It's not that important why. It's just that's the way it's done. You can convert centimeters of water to all different kinds of pressures, including torr and back and forth, but just the way it's done. So you just got to put it in your mind. Respiratory system, centimeters of water; cardiovascular system, millimeters of mercury. So the intrapleural pressure holds the lungs to the thoracic wall. If punctured, the lungs collapse, right? So we already talked about that. Alveolar pressure, P, the pressure, subscript ALV, alveolar, directly affects air movement. The pressure that drives inspiration and expiration is alveolar pressure. This is the one that drives inspiration and expiration. Now, all of the pressures are involved, but the direct driver of inspiration and expiration is the alveolar pressure. It can be negative during inspiration. It has to be negative. It's positive during expiration and 0 when there is no airflow. So important take-home message is this slide. 1, alveolar pressure drives inspiration and expiration. It's the most important pressure. 2, alveolar pressure can be negative on inspiration, positive on expiration, and 0 at no airflow. 3, intrapleural pressure is the pressure that holds the lungs open, right, from collapsing, because the pleural pressure is how you transmit the pleural fluid, and this pressure is how you transmit the rigidity of the chest wall, which wants to be at 60% TLC, to the lung. And this always has to be negative, and because it's always negative, your lungs always stay open. Okay, so those are the most important things from this slide. So differences between the alveolar and intrapleural pressure, right? You have what's called transpulmonary pressure, which is P subscript TP. TP stands for pleural pressure. And transpulmonary pressure is a type of transmural pressure, and a transmural pressure is a pressure across two areas, right? Two boundaries. A boundary, excuse me, between two areas across a boundary. So the transpulmonary pressure is always positive and represents the elastic recoil of the lungs. So the transpulmonary pressure wants to make the lungs collapse, right? The intrapleural pressure wants to hold the lungs open. So these forces balance, right? These forces balance, and you can think about the intrapleural pressure, it's not exactly right, is representing the pressure that is generated by the chest wall to keep it at the lungs open at 60% TLC, and the transpulmonary pressure, right? This would be the transpulmonary pressure being the recoil that wants to keep the lungs at 0% TLC, right? And they come to this happy median of 40% TLC. Number one rule, if transpulmonary pressure increases, so does lung volume. So does lung volume. Review of some gas laws. So here we have Boyle's law, and Boyle's law states that the pressure of a fixed number of gas molecules, right? So let's say that there's, I don't know, 10 gas molecules here, I'm not going to count them, is inversely proportional to the volume of the container at a constant temperature. So temperature is held constant. So the equation is P1 V1 equals P2 V2. So you have a system under compression versus non-compressive states, right? In a compressive state, you decrease the volume, pressure increases. In a decompression state, you increase the volume and decrease the pressure. So this explains the lung, right? Because in expiration, you decrease the volume and you increase the pressure, right? It becomes positive. In inspiration, so expiration, in inspiration, right, you increase the volume in the lungs, but you decrease the pressure. You need to have a negative alveolar pressure in order to bring air into the lungs. It's a negative pressure system, right? But in order for that to happen, transpulmonary pressure has to increase. So we go back. So transpulmonary pressure is always positive, Alveolar pressure is always negative. When you take in a breath, transpulmonary pressure increases, becomes more positive, and alveolar pressure becomes more negative. And that is explained by Boyle's law. Now the sequence of events, more stuff you need to have on the tip of your tongue that you just straight up have to memorize. There's stuff you have to memorize, which is straightforward, and that's not where people have most of the problems. And then there's stuff you just have to understand, and that's, again, going into the mechanics. So the sequence of events is thus. The diaphragm and the inspiratory intercostals contract. The thorax expands. The rib cage expands, right? The intrapleural pressure becomes subatmospheric, right? The intrapleural pressure becomes subatmospheric. Remember, the intrapleural pressure is always negative, so it drops even more. This increases the transpulmonary pressure, right? Remember, the transpulmonary pressure is always positive, so it goes up even more. The lungs expand, and then the lungs expanding decrease or make the alveolar pressure subatmospheric, and air flows in. So air flows into the lungs because the pressure inside the lungs is lower than atmospheric. Another thing I forgot to mention is no matter where you are on the planet, atmospheric, the air you breathe in is always the 0 point, right? It's 0. When you inspire, compared to the 0 point, the inside of your lungs, the alveoli, have to be negative. -1, -2, -3, -4, -5, -6 centimeters of water. When you expire, the pressures inside the lungs and the alveoli have to be positive. +1, +2, +3, +4, +5, +6, whatever the number is, centimeters of water. Expiration is exactly the opposite. The diaphragm and the inspiratory intercostal stop. Remember, this part is passive. Expiration is passive. So once the diaphragm and the inspiratory intercostals, stop contracting, the chest wall recoils. Intrapleural pressure moves back towards pre-inspiration value. Again, it's still negative. It's just not as negative. Transpulmonary pressure drops, decreases. It's still positive, it's just not as positive. The lungs recoil. The air in the alveoli becomes compressed, right? So when the air becomes compressed, right, when you increase the pressure, you're going to decrease volume. And so the alveolar pressure becomes greater than atmospheric, becomes positive, and air flows out. I think we'll stop here, and in the next lecture, we'll start talking about this diagram. This diagram I have nicknamed, so you're not going to hear this anyplace else. I just use this nickname to make an analogy, metaphor to Wigger's diagram. And this is what I look at as the Wigger's diagram for the respiratory system. It sort of is a diagram that brings all of the changes that occur into one diagram so that you can see them nice and neatly. So hopefully the overview for the respiratory system has been a successful one. Please listen to this lecture multiple times. Write down the things you need to memorize because you're going to have to memorize a lot. I've said this over and over this semester. That's step one, right? Get to the easy stuff. Make sure that you're doing that stuff a little bit every day, and then start trying to grapple with these more challenging conceptual these ideas, these concepts, which are not so easy to grapple with, but it becomes a lot easier if you have inspiration, expiration memorized, the anatomy memorized, the branching of all of the airways, right? And then volumes, which we haven't got to, in capacities. All right. Hopefully that was successful for you in terms of picking up some important information and knowing sort of where I'm heading, what direction I'm heading in for the respiratory system. Like I said, go over this, ask questions. I'll be in office hours, and I hope everybody's doing well. Have a great day.